everyone. Welcome to the international webinar on an overview of Big Data Warehouse Architect by IRAJ in association with ITR Group. On behalf of the entire organizing committee, I'm Isaac Behra, Organizing Secretary, would like to welcome you all for this virtual conference. Let me introduce our organization. The motto behind this non-profit association is to bridge the gap between students, professors, academics, and industrialists from multidiscipline. Apart from organizing various seminars, expert talks, and conferences, we have various highly rated multidisciplinary journals in the field of science, engineering, technology, and management. Since our inception, we have been arranged a various international conferences and various parts of the world like New York, London, Australia, Hong Kong, Dubai, Bangkok, Kuala Lumpur, India, etc. More than 1 lakh people across the globe are associates with us, and more than 5 lakh research papers have been presented and published during our journey. Today, I am glad to welcome you all as a member of this fastest growing network for the advancement of science and technology in terms of research and innovation. So today we have a very much fortunate to have one eminent professor who joined us as a guest and session chair. His name is Madhusudhan Reddy. He's working as an associate director, the Department of Application Development, and his company name is Santander Bank. He's working in Holmdel, New Jersey, USA. So can we start, sir?
Hey all, as it has been mentioned, my name is Madhusudhan Reddy Sureddy. I'm working as an associative director for Santander Bank with my experience predominantly with data warehousing technologies and big data warehouses. Today, as part of this webinar, I'm trying to cover an overview of big data warehouse architecture. The agenda, the way I'm going to cover the meeting is, first I'm going to explain what traditional data warehousing looks like. Then I'm going to go into the big data technologies, and then I'm going to provide the big data warehouse architecture. Starting with traditional data warehousing. Before going into traditional data warehousing, first we need to understand what OLTP systems are. OLTP basically stands for Online Transactional Processing. Online Transactional Processing systems are nothing but the examples like a bank or a mall or an e-commerce. Such businesses would require some systems to handle their daily transactional processing. To take an example, let's say as a person goes into a store to buy a few products, and he's gone to a mega grocery store. And when he goes to billing, there are many transactions which need to happen. Few of the transactions, like one, an invoice of the bill has to be generated. Second, product information has to be tagged to the invoice. Customers' loyalty cards might need to be updated. The total number of products which the customer has bought needs to be reduced out from the store. So all of these things are handled by something called as OLTP systems. So you can take OLTP systems are the front face for any business. And from a technology standpoint, OLTP systems have a front-end user interface application, and at the back end, you have something called as a database. Now let's talk about what a database is. Database, on a definition standpoint, is nothing but an organized collection of structured information or data, which is typically stored electronically in a computer system. And database always has something called as a database software program called as database management system, which runs on top of the database. Basically, DBMS serves as an interface between the database and the end user. The end user can be an application or an actual user. And what does this DBMS help you in doing? It helps you in easily retrieving, updating, and managing how the information is organized and optimized. Data within the common types of databases in operation today is typically modeled in a relational format. When I say a relational format, it means that you have rows and columns and something called as tables. And what does this do? It allows the data querying to be efficient. And most DBMS, or the most popular DBMS right now, are relational database management systems. Historically, we had something called as hierarchy database management systems, but predominantly right now we are using the RDBMS. And how is this DBMS making the interface and allowing you to easily retrieve the information and update the information? Is by using a query language called as SQL. SQL is the language which helps you in writing something called as a select statement to retrieve the data, then an insert statement to insert data, update data. So it does multiple operations and multiple commands which allow you to easily retrieve the information. Classic examples of these RDBMS include Oracle, Teradata, MySQL, etc. Now let's start with what is business intelligence and traditional data warehousing. Business intelligence, as the name suggests, it is the ability of gaining intelligence on the organizational data and utilizing this intelligence to make organizations strategic and tactical business decisions. It's basically you need to gain intelligence on the business so that you can grow your business. That's what business intelligence helps you to do. Now, deducing insights, let's say all of your business information is stored in your OLTP systems and maybe in their RDBMS. And in some cases, there could be other systems other than the OLTP systems which provide this information. So deducing insights on such raw, unformatted OLTP's data, which is both current and historical, could be a tedious task. So what does business intelligence do in those cases? Business intelligence brings in a layer between the OLTP systems and the business intelligence itself, which is called as a data warehouse. What does this data warehouse do? Data warehouse basically integrates the data from the various OLTP systems and other sources and stores it in a reportable structure. What do you mean by reportable structure? Reportable structure is nothing but the whole database is modeled or organized using the data warehousing or the data modeling principles of Bill Inman or Ralph Kimber. When I say Bill Inman, he was the father of data warehousing, and he was the one who introduced the concept of third normal form data modeling. And Ralph Kimball introduced the concept of star schema modeling, which allowed to easily and fastly retrieve data. So in simple terms, the concept is you have dimensions and facts. And in dimensions also, you have multiple types of dimensions, but predominantly data warehouses utilize something called as slowly changing dimensions type 1, type 2. And in the facts, mostly they are snapshot facts. And these data warehouses are loaded using two methodologies. One is the extraction, transformation, and loading. Then you have extraction, loading, and transformation. Then the next slide, I'm going to cover ELT, because we have a limited amount of time. So I would be covering the ELT methodology. Coming to where does the data warehouse store the information? Data warehouses store the information again in an RDBMS database like Oracle or Teradata. Coming to the traditional data warehousing architecture using the ELT model. So as I was mentioning, you have OLTP systems which provide all the information which needs to be loaded and insights needs to be generated. So OLTP systems, data is extracted out of the OLTP systems and files are produced out of it. And these files are loaded into something called as a staging area using, SQL provides functionalities like SQL loader. Then after the data which is loaded into the tables is integrated with various such tables from various other source systems and again transformed. When I say transformed, you need to merge it together. You might have to do some kind of aggregation. All of these things happen on that data. And how that is done? That is done using the database packages or procedures. Then this transformed data is loaded into something called as a data warehouse. And how this happens? because RDBMS provides you those easy functionalities of inserts, updates, and deletes. So data warehouse itself is loaded. Now, from this data warehouse, you utilize business intelligence apps like Tableau or BO to build some insights. Similarly, you can also feed downstream applications because many banks have other requirements which need to be fed in. So those downstream apps need to be fed in, and how those files or those things are generated is utilizing the SQL export functionality. So this is the traditional ELT model. Now let's take this use case quickly. I'll just walk you through this use case, which we would eventually be solving utilizing the big data warehouse architecture also. So the use case which we're gonna take is an organization has a requirement to produce feeds to a regulatory reporting application like Axiom for a banking system. What does this regulatory reporting application do? Basically, banks have a requirement to submit to federal agencies that their bank is at a good standing, and how they need to produce that information is by producing a document. And tools such as Axiom allow you to produce that document easily. But to produce that document, these applications generally get the data out of something called as a data warehouse. And how is that achieved? First, to get to this particular use case, first you model the whole banking data warehouse, potentially in a star schema format or the third normal format. Then you take a database, load that particular data model into that database. What do you mean by loading? You create the tables, which are nothing but the facts and the dimensions. Then, as I was pointing in the previous slide, the source files from the OLTP system are FTP'd onto the database server. Then you take those particular source files and load it into the staging tables. From the staging tables, you utilize packages and procedures and integrate and transform the data and eventually create multiple subtables in this particular process and load it finally into my data warehouse, which is nothing but facts and dimensions. And from those facts and dimensions, you join them together and produce the extract, whichever is needed by the Axiom front-end application. Again, you need to do some kind of select, joins, etc. to create that particular extract. And finally, you generate the file out, and that particular file is FTP to the regulatory reporting application. And the regulatory reporting application generates the regulatory report which is needed by the federal agencies. So to build such a use case, you have to flow through all of these steps. Now let's talk about what are the problems which we face with these traditional data warehousing approaches. One, traditional data warehousing cannot handle huge volumes of data. Two, real-time data ingestion and vending is a tedious process, or it's very hard to handle. Three, heterogeneous data sets like semi-structured and unstructured are impossible or very hard to handle. Finally, once the data volume starts growing, the fast access and processing speed is really slow. And why are these limitations in the traditional approach? The main reason for this is at an architectural level, RDBMS cannot handle such huge volumes. And even the current ETL processing technologies at an architectural level cannot handle huge volumes and all of these heterogeneous data sets. To handle such use cases, you need something called as the big data technologies. Now let's jump into what big data technologies are. First, before going into big data technologies, we need to first understand what big data is. Big data is nothing but a collection of data sets which are, as the name suggests, large and complex. What are the characteristics of big data? 5 V's form the big data. One is the volume, second is the velocity, third is the variety, fourth is the veracity, and fifth is the value. As the name suggests, volume is nothing but the amount of data which you would be processing is huge. Second, velocity is nothing but the pace at which the data needs to be pulled and vended out. Variety again would refer to the various types of data it can handle, structured, semi-structured, and unstructured. Veracity means if, in most cases with big data, there is a doubt or uncertainty in the data I'm loading, which could mean that there are some spaces, there is some nulls, etc. So veracity. Finally, value, meaning, do I really need to go to big data? Can the traditional approaches itself handle it? That's the value. The reason this value comes into picture is big data as a technology has a big overhead operationally, and then there are multiple challenges of big data processing, like how to capture it, curate it, store, search, share, transfer, analyze, and visualize this data. Because big data is it's an operationally, it's a huge thing to handle. So how did the whole big data come into play, and what was the starting point of these big data technologies? Apache Hadoop was the, I wouldn't say father, but it was the first technology which was introduced by the Apache Software Foundation. And they took the Google paper, which was presented sometime in the 2000s, and they built this whole framework using that particular Google paper, which was published. And what is Hadoop? Hadoop is not a programming language or a service. It's a platform or a framework which solves these big data problems. You can consider Hadoop as a suite which encompasses of number of services to ingest, store, analyze, and maintain the big data. So Hadoop, basically, how does this solve the main problems or the main issues which happen in the traditional approaches? First, it comes up with a concept called as HDFS, which allows you to store data of various formats across something called as a cluster. What does that mean? First, you need to store the data which can be pulled in a parallel format, because the main problem I'm trying to solve using big data is the speed. So you're basically breaking the whole data in and putting it into multiple servers or clusters. Second one is the yarn, which allows you to parallelly process this data which has been stored across HDFS. So meaning you first put the data across the cluster and then you process it over the cluster using the yarn. So the concept is doing it in parallel, and in future, when I want to increase the speed, you basically scale it across, like the number of servers are increased, the processing speed increase. That is the basic concept of Apache Hadoop. Now, Hadoop ecosystem, as I mentioned in the beginning, it's operationally, it's really huge, because as you see in this particular slide, there are multiple technologies as part of the Hadoop ecosystem. You have HDFS, which is nothing but the Hadoop distributed file system. You have Yarn, which is yet another resource negotiator. You have MapReduce, which runs data processing using programming. You have Kafka, which does stream processing. You have Spark, which does in-memory data processing. You have Flink, which again does stream processing and batch processing. You have BigHive, which provide data processing services. You have HBase, Mahout, Apache Drill, Zookeeper, Uzi, Flume, Scoop, Solar, Lucy, Numbari. So as you see in the slide, there are multiple technologies which cater to a specific requirement of the big data technologies. Like Uzi is basically allowing you to schedule it. Scoop allows you to pull data out of relational databases. Solar and Lucene are the ones which allow you to search it fast. So everything, and HBase is the NoSQL database of this cluster. Hive is again a SQL-like functionality which is produced. So everything has a specific purpose, and it's really hard when it comes to Hadoop ecosystems. So from a platform standpoint, even without a big data warehouse, Hadoop itself requires a good architecture to even venture into big data. So now let's start with the actual content of the webinar, which is big data warehouse. What is big data warehouse? As the name suggests, it has big data and you have a data warehouse. So it is an architecture for data management and organization which utilizes both the traditional data warehousing approach which we covered in the initial sections, and the modern big data technologies, which we just covered, to provide rapid analysis across a broad range of information types. Meaning my two requirements, which is nothing but speed, and my variety, which is nothing but various types of data. And why big data warehouse? Basically, I still need my traditional reporting, and also I would need my insight generation capabilities when I have something like logs or something which could not be handled by my traditional data warehouses. So it's nothing but it has to provide the flexibility of easy traditional reporting and also the additional capability of doing insights on raw data. Now let's look at the big data warehouse architecture. As you see in this particular picture, functionally there are total 6 blocks in the big data warehouse architecture. First one is the data ingestion block. Then you have the data preparation block. You have the data insights block. You have the metadata block, metadata HDFS directory structure block, and also the scheduling block. So data ingestion. Again, we would be covering in detail about each of these blocks in the subsequent sections. But data ingestion, as the name suggests, getting data from variety of sources like real-time and batch sources and bringing it down to the big data warehouse is what the data ingestion's functionality is. Data preparation. The main requirement of this data preparation block is to prepare the data and store it into the data warehouse. Finally, data insight block. It is nothing but the main functionality of this particular block is to allow the data for consumption and analytics. That's the requirement of the data insight blocks. Metadata. Why is metadata such a critical part of big data warehouses? Because there are everything in big data is files. So basically you are working on files. There is no database management system or anything which you're working on. You're basically looking at the files and schema is generated on the fly during reading. So metadata becomes very critical. Similarly, the HDFS directory structure also is very critical because everything is files. And finally, the final block is how do we schedule these particular jobs in big data warehouse. So these are the main functional blocks of the big data warehouse architecture. Now let's start with data ingestion. What kind of data lands into the big data warehouse? Structured, semi-structured, unstructured. Let's talk, we have been speaking about what these data types are, dwelling into what they are. Structured is nothing but the ones which have a defined format. Let's take the example. Examples are an XML or a database table because it has a specified schema, predefined schema for that particular entity. Semi-structured. Semi-structured is nothing but they have a schema, but it is very loosely defined. The classic example would be the spreadsheet, where you have grid of cells, but anything can put into the cell. You can put an alphabet into it or an integer into it. Anything you can put into that particular cell. So the schema is very loosely put in. Unstructured ones, they don't have a schema definition at all. Like it could be a plain text or an image. Now coming to the various patterns, which is nothing but the one which we could not handle in the traditional data warehousing are the real-time patterns. So what all should my data ingestion framework of the big data warehouse handle? It needs to handle both the real-time patterns and the batch patterns. And there will be further sub patterns when you talk about somebody's pushing it in or I'm trying to pull it in. So combinations will be one real-time batch with push and pull mechanisms. This particular slide is what covers the whole patterns and how big data warehouse handles it. So what happens in the data ingestion is the data is taken from the batch and real-time systems and put into something called as a landing layer. So in this case, in the big data warehouse terminology, a layer is nothing but a file which is stored in a schema format, which is nothing but it's not a database table. It's again a file at the backend. So we need to think when we go to big data warehouses, everything is a file. So now taking the example of real-time sources. Real-time sources could be, there is an application which wants to pull or which wants to push data on real time. That could be a classic example of real-time source, or a database which is constantly getting updated. So these two real-time in these two real-time cases, one, when it is an application, the application would be calling a API program which the organization needs to build, and that API program needs to have a RESTful features. What do you mean by RESTful features is it needs to have the get put functionalities which the REST services provides, similar to the regular JSON structures. So a RESTful API, and that particular RESTful API would utilize the Apache Kafka, because when people are trying to push it in, you need that speed of streaming also. That is where Kafka comes into the picture. So you go to the Apache Kafka streaming, and then you utilize either Spark or Storm or Flink, and then land it into the landing layer. So you basically drop it into that particular message turns into a file. Similarly, you could have databases. When it is a database which is constantly getting updated, there is again a technology in big data, which is nothing but Apache Flume agents, which allow you to pull the data out of these database logs and then put it into the landing layer. Same thing, not only database logs, regular logs can also be read through the Apache Flume agent, which again are put into the landing layer. Then there is the batch component, which is nothing but you have your OLTP systems, which either can produce the files which you require, which is at the bottom of the screen, where the files have already been extracted in the database. And again, those files again pass through the API which the organizations build. We will dwell further on why that API comes into play, but they will be put into the landing layer. In some cases, they do not provide the extracted data files. So again, big data provides a functionality, or in the ecosystem, you have something called as Apache Scoop, which allows you to pull the data from the databases and put it into the landing layer. So in summary, the data patterns are nothing but you have real-time data ingestion, asynchronous data ingestion, and the direct data pull. So that's what these all are: real-time. Second one is the asynchronous. Third one is the direct data pull. So what is the real-time data ingestion? As I was mentioning before, you build this API. What does this API do, and why do you need that API? We are bringing in this API because you need to understand the metadata of the file. So that is the reason you have this API which stores the metadata of the source, whichever is coming in, and puts it into a backend edge-based table which stores the metadata of the source, whichever is coming in. So you build a custom application which can respond to real-time source calls. Asynchronous data ingestion is nothing but the source is dropping files into a shared drive. Why does this need to go through the custom API? Because you again need to take the metadata of those files and put it into the edge-based table. Similarly, it basically checks for the flag files and the actual data file, and the flag file details are put into the metadata, and the files are moved into the landing area. So that's the part of the API. So API is basically needed either to get the RESTful functions or to handle these metadata handling functionalities. Finally, you have the data pull. Data pull is nothing but here in these cases, you use the Scoop or the Flume agents which connect to the source databases and put it into the landing layer. So that is about landing layer and data ingestion. What's data preparation? Data preparation is the block where the data is transformed and prepared for analytical and data processing needs. And there are two layers as part of the data preparation block. One is the structured layer, second is the curated layer. What is the structured layer? So when the files come from the respective source systems, they are put as is into the landing layer. When I say as is, there is no transformation happening. Everything in the string format is placed into the raw zone or the raw layer called as the landing layer. The second step of the process is changing them into something called as structured layer. What is structured layer? Basically, you change them into typed data structures. What do you mean by typed data structure? Like if the column could be an integer, you try to change that into the respective data type and put it into the typed data structures. So data from the landing layer is first moved into typed table structures in the structured layer. This layer is basically doing the first stage of transformation. How? By moving something, a string, into the typed data structure. Again, the landing layer, even the strange structure layer, is also a file. So a file is taken, a file is put in. But in the case of a structure layer, the file is converted into something called as a Parquet format. Apache Parquet again is a format which was deduced for what it does is it basically allows you, it's a columnar storage format which was predominantly used for reading, decompressing, and querying. Because one of the major thing is, though it is big data, you still need to put the data in a compressed format. Otherwise, the volume of the data blows out completely. Then from the structured layer, data is put into something called as a curated layer. Curated layer is the data warehouse in the big data warehouse architecture. Curated layer is the one which has the actual data model. Again, this data model again predominantly follows the concepts of Bill Inman or Ralph Kimball, where you have facts and dimensions. But there is a little change in how the dimensions and facts are utilized, which I will cover in the next slide. But curated layer is the place where the data from the structured layer is taken, it is integrated, it is transformed, it is data quality checked, and put into the data model format defined by your modelers. And again, curated layer is also a Parquet file. Now, how does the model differ from traditional data warehouses? Conceptually, the concept is the same. Like you could still have facts, dimensions, the same thing. But the major difference is the mutable changes. What do you mean by mutable changes? Update, append, and delete. So these things are a complex operation when it comes to big data stack. Why? Because you don't have those DBMS software which is running on top of the database, which handles this mutable changes in the traditional data warehousing or the traditional databases approach. That is the major thing which is causing a problem when it goes into the big data volumes. But that is the one which allows you to provide the functionality of the concepts which are available in data warehouses, which are really not needed when it comes to big data, because you are not really worried about storage, because the concept of slowly changing dimension type 1 or a type 2 is predominantly is needed because the volume of the dimensions can also blow up. That was the reason that came into the picture. But ideally speaking, in big data world, the concept of volume and speed is very relative because you have extremely high speed and you can store any amount of data. So the concept of mutable changes needs to be tweaked in the big data warehouse. And how is it tweaked is, there is no concept of slowly changing dimension type 1s and type 2s. Every dimension in the big data warehouse is turned into something called as a snapshot dimension. Basically, you eliminate the updates completely. So every time a record comes in, it will be stored as a new record, making it a snapshot. Facts are generally already snapshots, but in this case, facts are also snapshot, and there is never at least in the curated layer, you don't place aggregated facts because you don't want business users to later on have a problem. So you are always having the facts at the lowest level of detail before pre-aggregation. That's what you do. Now coming back to the keys, the generation of surrogate keys, because the integer sequence is a complex operation. Again, it's a very complex operation. So instead of integers, you use the concept of UUIDs or hashes, which allows you to provide the similar functionality as a surrogate key integer functionality. So predominantly, handling the mutable changes, especially the updates, is the differentiator between the traditional data model and the big data warehouse. And even the accumulating facts, they are also made insert only by creating a new state that symbolizes the end of the previous state rather than updating the previous state. So basically, all the updates are removed out and those all become insert operations. How? By making it into snapshots. Finally, data insights. This is the actual layer which is utilized by the downstreams for their consumptions. So in data insights also, you have two layers. One is the consumer layer, one is the analytics layer. As the name is suggesting, consumer layer contains the final data sets which can be consumed by the downstream applications or reporting tools. So consumer layer, as the name is suggesting, it provides an easy access point for consumers. This is similar to the data marts in the traditional data warehousing world. And this also sometimes contain the final downstream application formatted tables or files. And this is where you have the proper schema definitions and you require the SQL-like functionalities because somebody downstream might need it. So that is the reason you store the consumer layer in something called as Hive or Impala, which are the NoSQL versions of which are the SQL versions of the databases. And there you store it in partitional, and there is a concept called as external tables because they are used for vending. So what is this analytics layer? Analytics layer is the one which I was talking in the beginning of the big data warehouse slide, that this is the place where you allow your data scientists to analyze and experiment, because not everything can be modeled in the beginning. There could be multiple cases where you just have your files, you don't know what insights you want to build, and that is the experimentation which the scientists do and build those awesome insights for you, which can allow you in organizational growth. The classic examples are where Facebook, people are posting something in the Facebook, but those comments in the Facebook could show how your organization is being projected in the outside world. So that also brings excellent insights. So analytics layer provides that functionality for data scientists to explore. And obviously data scientists will have access to everything. Like they will have access to the landing layer, they will have access to the structure layer, they will have access to the curated layer, everything. But there's no point in having it in the consumer layer because consumer layer is again a subset of the curated layer. So they'll have access to all the layers in the data warehouse. And how are these insights generated? Normally, you can utilize Python, R, and SAS, but there is again one predominant difference when you generate data insights in big data warehouse, which is one, you don't bring data to processing. You bring processing to the data. What I mean by that is all of those complex calculations should be running inside the big data ecosystem rather than going outside and running it. Because I could have a Tableau reporting tool which is trying to pull data out of Hive. The Tableau, you shouldn't be pulling data into the Tableau server and running the aggregations or any kind of applications there. You should have done all of that processing in the big data space itself and maybe populated the finalized table into a Hive table, which is an aggregated version of whatever insights you want to produce, and then take that smaller volume table into the Hive and then project it for data visualization. So basically, processing has to be done in the big data ecosystem and it shouldn't be done in the analytics ecosystem, which you built, either it is R, SAS, or even Tableau. So it's basically bring the processing to the data is the major change when it comes to the big data warehouse. Now coming to metadata. Metadata is very critical because again, there are no tables and everything is a file, and all the data which comes from the sources, it needs to be, it needs to be looked at. What is the structure of the files? Everything has to be stored as part of your metadata, because if you do not have metadata, you might again be loading the same files again and again because you don't know where to check it for. So that is the reason keeping metadata of whatever is coming into the big data, big data ecosystem is very critical. The types of metadata could include what are the document ingestion process metadata, what is the document catalog, what's the Hadoop metadata, what's the data provenance metadata, what is the data set statistics metadata. So when I say Hadoop metadata, it could mean the HDFS directory structure metadata is also part of the Hadoop metadata. So coming to HDFS directory structure. Again, I've been mentioning it multiple times over the call that everything in big data is a file. So putting them in a proper structure is very critical, so that the access is properly maintained, auditing is available, everything is there. So the suggestion would be the directory structure should be organized in the order of data lifecycle, application, and age. What first thing is, you normally make it into data and user. Data is nothing but the finalized data sets. Users are nothing but the user related data sets. Then comes the various layers you have inside that. So in data, you have landing, structured, curated, consumer, analytics. So those are the base folders. Then you can again have underneath those folders at an application level. If you are building your big data for various applications, you can put application level folders under that. You can again then put the dated folders under that. So that's how the hierarchy has to start. Scheduling. Though Hadoop provides the scheduling tools like Uzi, our recommendation, my recommendation would be that you utilize the enterprise schedulers, because they still provide the functionality of kickstarting jobs in big data, because you could have OLTP systems which are running jobs and produce the files for you. So it is easy when you go with an enterprise scheduler to easily schedule between the OLTP systems and the big data jobs, rather than utilizing the Hadoop ecosystem's workflow and orchestration tools. Finally, the technology recommendations. So as you see, the block, the storage layer, the pattern, and what is the framework or the tool you utilize, and the programming language. The programming language choice is very clear. You have to, or at least from my standpoint, it's better to utilize Python, because Python has a beautiful project base which allows you to write a big program in a couple of lines. Like a program which you could do in any other programming language becomes a couple of lines, because there are multiple projects which are being developed in Python, and everything you think in your mind could have already been built, and a module might have been developed for it. So Python is the programming language, and from the processing or the framework standpoint, predominantly I don't think MapReduce should be utilized, and you should go with Apache Spark and Kafka, and file formats are either Parquet or Avro, and you should use Apache Scoop for data ingestion. Similarly, Hive or Impala when it comes to the consumer layer, and HBase when it comes to the metadata, and enterprise scheduler is the one which you'll be using for the schedulers. We just covered it, but this particular table just gives a recap on whatever we have discussed till this point. Now let's talk about the big data warehouse use case, which we discussed in the beginning of the call, which we built using the traditional data warehousing approach. What are the changes? Yes, you still need to build the logical data model for the banking data warehouse, which is nothing but your curated layer. But here, the change is all the dimensions and facts should become snapshot structures. They cannot be the traditional structures of SCD type 1s and type 2s. Second thing, you require a API which will be putting the files from, the source files would first be sent into something called as a shared drive or a file system. And from the file system, you run a command to put it into the HDFS area. And you build those custom APIs to build metadata on top of it. And still you need to run the command to put it into the HDFS file system. So that becomes your basic landing layer. Then you convert these landing layer files into the structured typed data structure Parquet files using Python programming. Previously, it could just be a simple SQL loader command, but again, you become Python programming here. And then the structured source files are converted into the data model Parquet files, which is nothing but the data warehouse model using Python programming, and stored into the curated layer or the data warehouse. From the data warehouse, you take the regulatory reporting needs and convert that into the regulatory reporting format, again using Python and Spark, and load it into the Hive tables in the consumer layer. And Hive tables are extracted out into CSV files and again sent into a shared drive. And from the shared drive, they are FTP'd into the respective applications. It's a major paradigm shift because you have to build everything through Python programming and Spark, but you again have to, it comes down to the value, whether this particular use case is really helpful for you and you do meet those 5 V's which allow you to go into the big data warehouse. But when you go into the big data warehouse, this is the approach which you should be following. I think that ends the overview of the big data warehouse architecture.
Thank you, Professor, for attending the virtual conference today. I would like to thank all our sponsors and coordinators. I would also like to thank our president. We're happy to hear comments and compliments or suggestions at our Facebook and Twitter page and also our YouTube channel. Thank you, Professor, for joining today.
Thank you so much.
Thank you.